Swayam Prabha. Digital India. Educated India.
So, at the outset, I would like to thank the organizers of this conference, SDCS, for making me a part of this endeavor, especially Lurdiraj, Sanjay, and Aswini, and their team, of course, the whole team. I'm delighted to dedicate this talk to Professor Sattamurthy on his 75th birth anniversary. I've deliberately chosen this topic as Professor Sattamurthy has been actively engaged in this type of, say, calculations. Of course, he is taking different AIML versions and applying it to different types of physicochemical problems. So here, I will first clarify what exactly do I mean by the soft computing perspective. So within quotes, what we would like to tell as the hard computing. So depending on the, say, length scale and the time scale of the system or the process you have been tackling. So either you use classical mechanics, quantum mechanics, statistical mechanics, or a cruder version like molecular mechanics or any other variant. You need to solve a differential equation or an integral differential equation, or at least, let's say, you solve some kind of eigenvalue, eigenvector equation. There you need to, say, formulate get the equations, if necessary, go for certain approximations, because only a minuscule number of problems can be solved analytically. And there, you just do the numerical analysis, write large computer programs, and then solve them. You have to think about your computer power, etc., etc. But now, what I want to mean here, without solving technically any given such differential, integral differential, or these type of equations, we will have kind of pattern recognition, and we will make use of certain, let's say, natural or biological say processes which we have been seeing in our day-to-day life, and try to formulate certain steps so that in our own way, as I told you, that the same problem can be tackled in different ways. And here you have various deep learning, or in a general sense, a machine learning technique, in order to simulate those biological or natural processes. And there, depending on which particular biological process or natural process we are looking into, so there are several possible such algorithms. Say, like you can have, of course, the most popular deep learning technique is your neural network, and it has several variations also now. And also you can have like particle swarm optimization, artificial bee colony, bonobo optimizer, and several others. Now here, what we are trying to do in a given setup, in fact, what we tried to develop, we have seen that in principle, you can prepare several hybrid modes of, let's say, you can combine different types of machine learning or deep learning protocols and generate robust, say, soft computing platforms using these. In addition, let's say, you can add DFT or atom-centered density matrix propagation, and you generate really robust, say, soft computing techniques. And we have tried several different types of such techniques and applied to also various types of problems like getting the molecular structure, the geometry, let's say the global optimization, then we did toxicity prediction, chemical reactivity analysis, aromaticity, and so on and so forth. But here, I have chosen a specific type of problem, that is global optimization, and I will tell you about a specific soft computing technique which we used in order to solve. In fact, we have used several others for solving this global optimization problem, but we'll tell you one particular technique which we have used for this global optimization. Okay, so first I will just tell you, this known to this audience of course, about the global optimization. What exactly do we do? So we have started with a very simple potential energy curve of a diatomic molecule, and it is near the equilibrium geometry where it is harmonic in nature. So this is your equilibrium structure, optimally, say optimized structure, and this is the nuclear potential energy, and these are internuclear distance. So suppose we start with a given structure. This I refers to, small I refers to input structure, and you know that the potential has for harmonic, this has this form, and at this particular point, if I take the slope, we know that you get this one, it's related to force basically, and then if you take the second derivative, that is related to the Hessian, with the bond force constant. For a simple harmonic oscillator, of course, it doesn't depend on, say, bond length or the internuclear distance. But of course, for an harmonic oscillator, there would be some dependence, but if you go for some iterative step, you can update it. Now here, you can see, if I want to write this one, and for k I substitute this, I will get this particular equation. And now I can write this Rho here. This is your output, let's say input minus, say, first derivative by the second derivative. In a multidimensional potential energy surface, I'm considering this as the energy, because the kinetic energy doesn't depend on the position, and I'm writing R as the Q. So this is a general, let's say, Q vector. This is your input structure, and let's say equilibrium structure is given by this. So basically the same equation, I can write it as the same equation, Q0, Qo is Qi minus H inverse G. Okay, so G is the gradient matrix and H is the Hermitian matrix. But the major problem is for a simple diatomic, the problem is not the severe, but for a polyatomic molecule, you'll see that if you want to get this type of potential energy, it's basically projection of the surface. This will pass through several maxima and minima, and one of them is your global maximum, another is global minimum, and you want to find out this one. But there lies a problem in global optimization techniques. Say, here in all those extremal points, of course, the first derivative is 0, and for minimum, the second derivative is positive, for maximum, it is negative. Now, for numerical solution, suppose if I write this first derivative as gx, that is 0. So at point xi, any given point, input point, where gxi is not 0, that means somewhere over here or somewhere over here, I can write that in the neighborhood of gx equal to 0, I will just simply expand this gxi plus h as Taylor first order up to first order term. Gxi is h g prime x equal to 0, or h is minus gx by g prime x. So xi plus h is xi minus gxi by g, because this is your h. So I can write it xi plus 1 is xi minus gxi by g prime xi. Now what we do generally, we just iteratively solve this problem But the problem here is, say in this GXI, when it reaches any one of these, say, external points, this becomes 0. So after that, it doesn't matter how many times do you iterate, it gets stuck. Your xi plus 1 will never get updated because it has reached the point. So this is the problem with this type of iterative techniques. And you'll call it that your typical iteration or the search gets stuck in any one of these local minima. And this is a standard problem in global map optimization. So you'll get stuck over here. So what you have to do? So we know there are various techniques like simulated annealing, heat it, across the barrier, and ultimately you will have to come to this. But now we will see that we will make use of certain soft computing techniques in order to go for the global optimization. We will just throw the system out of the local minima and go towards the global minima. So this is one of the invited perspective article of in JPCL. We published on the application of soft computing techniques for the global optimization. And here, as you can see, so these are various possible, so this landscape, you have these minima, local, global, this maxima, and these are different types of soft computing techniques like particle swarm optimization, then artificial bee colony algorithm, and firefly algorithm. We have used many of them. In fact, this artificial bee colony algorithm and DFT ADMP combination we have published just now in JCTC. There is one special issue of theoretical and computational chemistry in Asia. So in that issue we published. So first I will tell you a little bit about the artificial neural network. So the natural human brain, let's say it gets the information by various dendrites, and it passes by axons, and then you have the synaptic links through which it gets connected to another cell, and this way the information propagates within the brain. Here, in order to make use of this say performance of human brain, if you want to have some kind of computational approach, there you get the artificial neural network. Basically, it's a kind of deep learning type technique. So here you have various inputs coming. You just find out the total input what is coming, and not all information your brain wants to keep forever. So there are bias. So, and there are weights also. Some of the information would be considered to be more important than the others, and accordingly, ultimately the output will be there. So this is the simplest possible model. So you have say input signals x1 to xn, and these are various weights. This is the bias. So you get resultant input signal, and there is some activation function that brain doesn't want to keep all information whatever is dumped into it. So there is some activation function, and ultimately the output will come into the picture. So you get input signal, these are the weights, and V is the biasing term. So ultimately what you do, so net, what is the weight and how much, what is the input? So you get a kind of bilinear form, and that gives you this type of scalar product of two vectors which will be there. So this is the product of xi, y. This will be fed to the neuron, which sums them up to produce the net input. Now there are several neurons. For jth neuron, you get this one, and you are summing over this xi, yi terms. And this neuron J compares net J with a threshold parameter, because it will always think that which information is important to me and which information is not important to me, and accordingly, and also how much is the importance of that particular information, that would be given by this type of parameter threshold. And here you get various types of such activation functions, And we'll see that the sigmoid function commonly used because it's close to the biological neurons. So this is on single layer perceptron, and here you can see that weights are also changing with the inputs and the outputs both. So what we do in this case, so initial weights, we take the random weights, the output pattern known for the known input pattern. So you are going towards a supervised learning. For a given problem, let's say for a given set of inputs, you know the corresponding output. Then output matches the target, weight matrix remains unaltered. Otherwise, you make certain changes and change the weights. Okay? So it's very simple iterative technique. You just construct a model with different types of inputs, weights, and biases, and maybe certain hidden layers, and then you just try to generate the output through that ANN model and compare with the known output, because it's a supervised learning and label data. So you know the output for a given set of inputs. If it doesn't, so you go back and change the weights, and this is standard iterative protocol which you can do it yourself, and ultimately within a given tolerance, say the outputs will match within a given tolerance. So you just simply consider that to be your model. Now for a similar problem, you can use that already existing model, and there you don't need the level data to start with. You generate your own output via the standard set NN model. So these are the backpropagation technique details. In fact, there is a sophisticated cousin, a convolutional neural network. So where you have a local receptive field, a shared weights and activation and pooling, and then you have the convolution. And here also you have the forward and backward propagation. But here, these neurons have weights and biases which are same for all hidden layers. So that is a peculiar feature of the CNNs. So as I don't have much time, I just skip the CNN part. So now this is something what we have used for the global optimization. It's a swarm intelligence. So here you can see what do we mean by a swarm. It's like the flocks of birds, swarms of bees, colonies of fireflies, or schools of fishes, etc. You can see there is the behavioral pattern of these flying birds or others. And in fact, there are different types of such models which we had made use of for various types of problems. So a collective motion of animals displaying a structural border. The collection moves as a single entity despite occasional changes in shape and size. So the whole stuff is behaving like a single entity. Now, in order to do this, and another is the collective or the swarm intelligence is superior to the sum of intelligence of all individual, which helps the swarm to accomplish a task too hard for an individual. So swarm can do it in a much better way, which say single individual cannot do. So emergence of collective behavior depends on, so these are the say important steps which you can from the outset create, so that you can assume that the swarm behavior can be simulated with, is it? Okay, so you have homogeneity, locality, collisional avoidance, velocity matching, and flock centering. So I will just simply tell you the problem where we have made use of this. So we have used this determination of stable structure of clusters using CNN and PSO. And here also we have made use of DFT as well as ADMP simulation. So here what you can do, first we start with a given structure of the typical flock, and this is for, let's say, any atomic cluster which has different coordinates of various atoms present in the cluster. And we did a single point. So first we start with 100 such clusters, and we did DFT single point calculations with 100 clusters with different geometries. So I calculate the single point DFT calculations, and then I train my CNN model to get a model which can just give me the output structure properly from the corresponding input structure. The output, let's say the energy, etc., that is my function which I am trying to minimize. And in this case, what is happening, say I have the CNN model. After that, what we introduced from our side, that for a given structure out of starting 100, I run some atom center density matrix propagation simulation run, and I can generate, let's say, 1,000 such structures starting from one input structure. So altogether, my input base has become very large, 100 into 1,000 number of initial structures, which we call the population. So the population was generated through ADMP simulation. And energies of all of them now are governed by, say, CNN. And CNN is giving me the corresponding, so it was trained originally for only 100 using single point DFT calculation. Now I am not doing any more calculation. So CNN model is giving me 100 to 100 into 1,000 number of such this type of population. And here, once I get all the energy values and everything, I apply particle swarm optimization technique. So that will basically minimize the energy. That is the typical objective function for me. And ultimately, we can generate the structures. And at the end, when I get the final minimized structures using particle swarm optimization technique, I do some kind of post-processing where the final structure generated from the PSO is then sent to Gaussian 09 package and to get its optimized geometry in the post-processing step. But surprisingly, what we have seen, so doing all those steps like starting with 100 structures, doing DFT, single point calculation, training a CNN model, and getting 100 to 1,000 by ADMP, and ultimately generating the energies of all of them, throwing it to PSO algorithm, and ultimately getting the final structures. The structures, what we are getting out of it, even after post-processing through final DFT optimization, we see they are very, very close. So that gives us the confidence. And we have started with different types of clusters. So, and these are this metric representation, etc. So here you can see that we started with, let's say, for a carbon cluster, C6, C5 cluster over here. So different types of clusters we have chosen. So these are all random. And after these random 100 clusters, we generated ADMP clusters. So ultimately you have 100 into 1,000 such clusters. They are making the population. And here you can see your, say, inputs are like this, x0, x1, x2, they are the like x, y, z directions, etc. So you start from this in a given space, and this space also we have tried, it may be a mu space, it may be a gamma space. That means you can consider in a given space several points, or you can expand the dimensionality of the space and consider only single point to depict a population. So in a mu space, like in statistical mechanics, you put several points, and each point will give you specific particle. But you can get a total population of particles if you go to the extended space where you get typical gamma space sort of stuff in statistical mechanics. And we have shown that you can apply both of them and you get the similar results. So this is, so what is the overall flow chart of the PSA approach? So you initialize the particle with random coordinates, perform ADMP to generate 1,001 configurations for each structure, compute energy of PSO particles using CNN, and then update the positions and the velocity with the PSO, and ultimately you check whether it has converged, etc., and do finally the post-processing. So this is so you see the result. We have done it for several systems, and also, so as the referees have told for various papers, that you have to compare with the known. So we have done it with several stuff, and it takes much less time and energetically also much superior to standard like simulated annealing, basin hopping, and many other well-known say protocols. And we have shown that our method, what we have proposed over here, is much more robust, and it can give you the structures and the corresponding energy values, say much better than those values. This is something what I have deliberately chosen because our group had written a paper with Professor Sattamurthy. So here you can see these are the interesting polynitrogen molecules, N42 minus and N64 minus less N42 minus. We have something like cyclobutadiene, N64 minus. We have something like benzene, but they have interesting properties that also we have shown. One like this is having multiple aromaticity because it has both sigma aromaticity and pi aromaticity. On the other hand, this molecule exhibits what is called conflicting aromaticity because it is say sigma aromatic and pi anti-aromatic. So depending on which electrons you are probing, the molecule would exhibit its aromatic character or anti-aromatic character. They are today's knowledge, we call them molecules possessing conflicting aromaticity. And we did these structures of these molecules. And also another important aspect is you can get not only one structure, so which is the problem with the other types of protocols, that you can generate several structures, low-lying structures and also high-energy structures, which you can get it through solution using, let's say, DFT. So it is not the only the lowest energy structure. You will get the structures, say the lowest energy, the next higher energy, and so on and so forth. So we could generate the whole spectrum, at least some low-lying energy states. So these are other algorithms which I don't have time to tell. We have applied this Firefly algorithm, etc., for the solution of similar types of problems or other types of problems as well. And different types of methods you need to say adopt in order to solve, let's say, chemical reactivity problem or toxicity problem and other. But in general, you can make use of these protocols. And here you can see we are not solving any, say, ab initio or whatever in DFT or any type of electronic structure calculation methods. We are just simply taking it through certain rules which can be used to simulate the, say, behavior of various biological systems or maybe producing certain materials. Thank you very much.
Swayam Prabha, Digital India, Educated India.